Before we start, I just wanted to remind everyone that this afternoon we have the open problem session, and you can sign up either through this short URL or you get an email.
Okay, so the first speaker today is Andrea Montanari, who will talk about a very controversial topic.
Okay, thanks for setting the stage. Okay, so I think a good starting point for this talk is explaining the title, right? So this is joint work with Behrooz Ghorbani and Hamid Javadi, who are two students in Stanford. Right, so let me start by explaining the title. So what is topic models? Topic. So this is a popular way of modeling data sets that are formed, for instance, of documents. x1, x2, xn. So these are representing as vectors in some high-dimensional space. And the idea is that each of these documents is a mixture. So the mixture of topics h tilde 1, h tilde k, and these are also vector in RD. So think, for instance, that these are word counts for a dictionary in documents in a certain corpus. And the way this mixture is constructed is as follows. I construct a matrix that is a matrix whose rows has the vector x1 to xn. Okay, so this is a matrix that is n by d, and then I declare that this matrix is generated as some coefficient that I'll call square root of beta over d times w h transpose plus z. Okay, so here w is a matrix w1, wn. So it's a skinny matrix. This is k, and this is n. And each of these wi is just a probability vector. Okay, so wij, sum over j is 1, and wij is non-negative. And this matrix H, I'll also write for the rows of H, H1 to HD, okay? And each column of this represents a topic, okay? So this is, say, D by K. And you can think of Z as noise or whatever is not captured by this, WH transpose model. Okay, so this kind of model was really made popular, in particular by a very well-known paper by David Bly, Andrew Ng, and Mike Jordan in 2003. Okay, about latent Dirichlet allocations. Okay, and what did they introduce? One main idea of the paper was to introduce a probabilistic model, a Bayesian model for the weights, and in particular, the main assumption there, the main idea there was that the weights wi, so the rows of this, were IID Dirichlet with some parameter nu. Okay, so the Dirichlet distribution is a probability distribution over probability vectors in k dimension, is parameterized by k parameters, nu1 to nu k. Okay, so here I will simplify a little bit the model of Bly, Ng, and Jordan for being able to do a bit more calculations. So in particular, I'll take these parameters nu to be all equals. So nu, the vector nu to be nu blah, 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 nu. So all the parameters of the Dirichlet are equal. So in particular, the density of the Dirichlet that I'll indicate by Q0 of W is basically, apart from a constant, is the product over I1 to K, Wi to the nu minus 1 times the indicator function of W being a probability vector in k dimension. Okay? And the second simplification, and I'll make, okay, if you think of what was my motivation, this matrix X is a matrix of word counts, so this should be integer, should be non-negative integers. Here I'll do something a bit simpler. I'll take this X to be real, and the matrix, the columns of H, or the entries of H, to be IID normal. Okay. So the prior that I'll put of H is very simple, is normal, and also the noise, my noise will also be Gaussian. Okay. Of course, the original model, the noise is Poisson. Okay. But as you will see, I don't think this really changes much things. Okay. And the question in this problem is, of course, given what realization of this matrix X, estimate the factors H and W. So the factors H gives you the topics, and W the decompositions of the documents into topics. Okay, and starting with this paper, really, one method that became very popular was called variational inference. Okay, so this explains other part of the title. So I explain what topic models are, what is variational inference. Well, the idea is I want to minimize, I want to do Bayesian inference, so we want to estimate the posterior of H and W given observation X. But I want to translate this into an optimization problem. So instead of doing Monte Carlo, for instance, I want to write it as a minimization problem. And the way I do it, I try to minimize the Kullback-Leibler divergence between a probability distribution Q hat and the posterior of H and W given X. Okay. Now, this is an optimization problem, but it's an optimization problem in extremely high dimensional space, because Q is a probability distribution over all of these numbers, so it's exponentially large, but you minimize it over a restricted set of probability distribution. You minimize it over a probability distribution that takes the form QHW equal product I1 to D of Qi of Hi, product A1 to N, Q tilde A of WA. So you say, I cannot possibly solve an optimization problem over a space of exponentially many dimensions. I restrict only on probability distribution that factorize over the rows of H and the rows of W. Okay? So this is the assumption. Once you write it in this way, okay, the other observation you notice is that this Kullback-Leibler divergence can be computed apart from constants, W given X. So this takes the following form, is the expectation with respect to Q hat of log of Q hat of H and W minus the expectation with respect to Q hat of log of P of X given H and W minus the expectation with respect to Q hat of log PH minus the expectation with respect to Q hat of log PW plus constant. Okay. And all of these are things that once you have a handle, in particular, if you take Q hat to be factorized, all of these are things that you can compute. The constant is the logarithm of P of X. This is something that you can compute, but all the other terms are objects that you can compute. And now you get an objective function that is very nice. I mean, it's not very nice. It's non-convex, but if you can minimize it, and if this assumption is good, it holds the promise of translating a Bayesian problem into an optimization problem. So the problem of computing the marginals into the problem of solving optimization problem. Okay. So is this clear, more or less, or is it clear? So this is, very short introduction to topic models and to variational inference. So the way they minimize this then is basically they do alternate minimization. You notice that this is convex in the Q and convex in the Q hat. And so you minimize with respect to the Q and then you minimize with respect to Q hat and you alternate. Okay? So minimized by alternating. Minimization. So you minimize with respect to the Q and the Q hat, etc.
Maybe let's keep it.
Let's keep it. Okay. 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 So I'll write here. All right. So the question that I want to answer is, does it work? And to explain the work, actually, so this is based on a paper that we hopefully will be out in a couple of weeks. I decided that I will explain a simpler example. And once you understand what happens in this example, it should be clear what is the result in general. It's more complicated to do calculations, but basically the same phenomenon. And the simpler example is this Z2 sync model. All right, so what is this model? It's a very simple toy model. You have a matrix that you observe, and this is a rank 1 matrix plus noise. The noise is a matrix W. It's a matrix W that has entry WII. So this is a matrix n by n. The matrix W has entry IID normal 0, 2 over n on the diagonal, and out of the diagonal normal 0, 1 over n. And the important thing is that the vector sigma is a plus minus 1 vector. Okay? Okay, so a lot is known about, so the problem here is you're given a realization of x and want to estimate sigma, okay? And, it's a very, it's much simpler than this, of course, because the distribution of the factors is very simple, but bears some resemblance. It's a low-rank matrix plus some noise. Okay? So problem, estimate sigma from x.
So you don't want to put this in a Bayesian framework?
Yeah.
Okay.
So, so the distribution of sigma is uniform over the hypercube, and the observation is just what I said. Okay. So what is the optimal Bayes accuracy? So this is well known. It's well known in this model what is the optimal way, the optimal error that you can achieve on sigma when n goes to infinity, and this was solved in two papers. So there is one paper that is it's explained in a different language, and it doesn't talk about estimation, but basically contains many of the results. And then there is a paper with Yash Deshpande and Emmanuel, 2016, and something that you can prove, or a corollary of these two papers, is the following lemma for any. Okay, this is actually can be proved even much easier for any sigma hat. So for any estimator sigma hat, so this is something that takes matrices and spits out vectors. If lambda less or equal than 1, then lim sup n to infinity sigma hat of x, sigma divided by, say, sigma at sigma is equal to 0. Okay, so this lemma is saying the following: give me any estimator, any possible algorithm, and compute the correlation with the truth. When n goes to infinity, this is asymptotically decorrelated, asymptotically orthogonal to the true vector. So you cannot achieve anything non-trivial. So now we know, and vice versa, this is tight in the sense that for lambda bigger than 1, it's easy to show that you can achieve positive thing. But for this talk, I only need this very simple fact. Okay. Now let's try to do variational inference on this model. Okay, what this means, following what I was saying here, what this means, I take a posterior, Q sigma, a postulated posterior, and assume that this factorizes. So now one nice thing about now the distribution plus minus 1, the fact that the sigmas are plus minus 1, is that each of these marginals is actually a one-dimensional object. It's parameterized by one number, its expectation. So I'll parameterize it by its expectation. So Qi of sigma I is 1 plus mi over 2. Right? So I parameterize this two-dimensional distribution by this number mi. Now if you do a little calculation, you obtain that for such a Q hat, the KL divergence between Q hat and P of sigma given x is equal to some, of course, is equal to some function of m plus constant. And the function of m, you can write it explicitly.
That's 1 plus sigma I mi?
Yeah, okay, plus 1. Thank you. Okay, so this function is very simple, is minus lambda over 2 m x0 m minus sum over I 1 to n h of mi, where, well, what is x0 is basically x where I put the diagonal equal to 0. Okay, so I replace the diagonal. It doesn't really matter, but the diagonal is replaced by zeros. And then h is just the entropy function. H of m is simply minus 1 plus x over 2 log 1 plus x over 2 minus 1 minus x over 2 log 1 minus x over 2. Okay. So this is just a three-line calculation. From this definition, you plug in these ansatz, and you get this free energy, this KL divergence. So of course, this is the first piece. So this is a nice function, right? It makes a lot of sense. The first piece is basically the maximum likelihood objective where you just replaced the plus minus 1 variable with variables in the interval 0, 1. And then this is a kind of entropy penalization. And notice that the maximum likelihood has a weight lambda in front of it, which means if the signal is very strong, go with the maximum likelihood. And then instead, if the signal is weak, you should go towards 0. This is minimized when all the m are equal to 0, so by the uniform posterior. So this piece makes a lot of sense. It says when the signal is not strong, just reply, estimate everything with 0. So this thing makes sense. So you want to minimize it over plus minus 1 to the m. And what you expect is that for lambda less or equal than 1, in view of this lemma, posterior should be approximately uniform. So this is the intuition. This lemma says if this is a good approximation for lambda small, the posterior should be uniform because no estimator can tell me anything that is positive correlation, right? Okay, so you start doing calculation, and the first thing that you notice is that if I look at the point 0, okay, so this is just the center of the hypercube. This is a stationary point. It's a critical point. So it's a critical point. In what sense? In the sense that if you look at the gradient of this at m star, it's always equal to 0. So you can call this the uninformative stationary point, the uninformative critical point. This is saying, it's a critical point of this free energy that is telling, okay, I have no information about the system, so you compute the gradient, but okay, you took calculus, so you can compute also the Hessian. I took calculus. Okay, you compute the Hessian and you get this. Very simple, right? This is quadratic, and this is a separable function. You have just to compute the second derivative of this function at x equals 0. That is not difficult, is 1. So this comes from this piece, and this comes from this piece. Okay? Okay, so this is basically, this 0 is setting things to 0 on the diagonal. It doesn't really matter. It's negligible if I replace it with the real x, right? And now, of course, you want to check whether the Hessian is positive semi-definite or not, right? Now, the nice thing is that I know pretty much everything about the spectrum of this matrix X. Okay, this is something that has been studied in in hundreds of papers in probability theory, and one thing that is known is this phase transition phenomenon, that if you look at lambda max of this matrix X, so this is a rank 1 deformation of a Wigner matrix. This is 2 if lambda is smaller or equal than 1, and lambda plus lambda minus 1 otherwise. Right? So you substitute there, and you obtain that lim n to infinity of the minimum guy. What is interesting is the minimum, because we want to understand whether this is really a minimum or not. This is what is 1 minus 2 lambda if lambda less or equal than 1, and minus lambda square otherwise. Aha! Something is happening. What's happening? Something troubling is happening here. So what's happening here is that when lambda crosses 1/2, this is becoming negative, right? So m star becomes unstable for lambda bigger than 1/2. Okay, and so okay, now you can do a little proposition. This is really all elementary. For lambda bigger than 1/2, any without probability, any local mean of f. Let's call it m hat, has 1 over n norm m hat bigger or equal than a constant. So for lambda bigger than 1/2, if you try to minimize this free energy, you get something that is pretty far from 0. On average, all the entries of m hat will be of order 1. So it's telling you that the posterior, okay, so this means that if you do variational inference, the posterior is telling you this is not uniform. I have a signal. But the m hat, where it will, in what direction will be in a direction that is completely uncorrelated with the true vector, because we have this lemma that tells us that it cannot be possibly correlated with true vector. So between 1/2 and 1, if you solve variational inference, what variational inferences tell you is, I believe that there is a signal, but the estimate that it gives you is pure garbage. Okay? So now I could more or less finish the talk here, but let me add something. So the same happens for topic models. Alright, so the calculation is more complicated a little bit, but
You know what happens for the global minimum? I mean, somehow if the spatial optimization is meaningful, the global minimum should have some meaning, right? But
I don't know where is the global minimum. But of course, this is true for any local minimum. So a global minimum, in my sense of interpretation, it's also a local minimum. But
on some level, it's not a failure of local search getting stuck in local minima, but it's a failure of this paradigm, right?
Yeah. See, this is what I'm saying. Even if you are able to, I don't know if you are able to optimize. That's a difficult problem. Can you optimize this non-convex function? I don't know, frankly. But I can tell you this, that even if you optimize it optimally, you get garbage out of it in this interval of lambda. Of course, if lambda is very large in this simple model, then you will get a good signal. But if lambda is very large, you can do pretty much anything.
So then what's the problem that you did this ansatz, this product thing?
Yeah, so the problem is, of course, it's these ansatz.
Sorry, so I'm a little confused here. So your message here is that if lambda is between 1/2 and, your message is really about when lambda is between 1/2 and
Right.
1. And what you're saying is that you have a procedure that seems to indicate that there's signal when there's really not, right?
Right.
Okay, so what happens when lambda is larger than 1? Because, okay, it gives you garbage, but why would you trust it? Lambda is less than 1 anyway.
If you have a real data set, you don't know if lambda is bigger than 1 or lambda. You run it, you get an answer.
Sure, but is there any procedure? So here you're
Okay,
any procedure that will tell you?
Yeah, of course. In this model there is, and of course actually in this model there is a procedure, for instance, in this paper that gives you the base optimal estimate up to, relative. So it gives you the base optimal, scalar product, for instance, or the base optimal mean square error.
Isn't that 0? I'm confused now.
Sorry? Okay, for lambda less than 1 is 0, so there is a procedure that for lambda less than 1 achieves this, and for lambda bigger than 1 achieved the best that you can achieve.
Okay, but you haven't told us what happens for lambda larger than 1. What happens, right?
Okay, I cannot tell you, I don't know, but for lambda big enough, you would expect that it works, right? Now, what happens, so bigger than a constant? What happens between 1 and a big constant, I don't know, right? But I would expect is that lambda is 1 plus epsilon, it will still be pretty much uncorrelated, right? Or it will be not particularly good.
Perhaps a different way to ask a similar question. So if lambda is less than 1, is there a procedure that actually says, hey, I actually have garbage? Like,
well, you can, if the model is true, you can, for instance, test the largest eigenvalue of the matrix.
okay.
Good old. and you test it again 2. If it is smaller than 2, I mean, if it is smaller than 2 epsilon, you say there is no signal.
Andrea?
Yeah.
Why is this theorem true? So it's true, but what's the underlying reason? Because we know that below the critical thresholds, the Gibbs measure will decompose into, it will be asymptotic.
Oh, okay, so this is start to be tricky, and this has to do with, so it's true that it's asymptotically separable. So this statement, this statement is not true in this form, but is true in the weaker form, or is expected, in the sense that, if you look at finite dimensional marginals, so joint marginals of any k subset of variables, this is asymptotically true. But now if you compute this, so you will say, okay, this is sufficient for computing this object, it's true, but the correlations gives a correction term. So this is what appears in the top free energy. So you know what these things are. And in fact, if you do with the top free energy, then it becomes stable. Okay. Any other question? Okay, so perhaps let me briefly talk about what happens with the topic models. Okay, so first step. So let's try to redo the same calculation that we did here. So I will not do the whole calculation. Information theoretic limits. So these have been studied recently. So there is a paper by Leo Miolan that really applies to this setting, and there is a related work by Lelarge, Miolan, by Barbier et al. 2016. That deal. So the paper that you need is this one, and this paper, okay, gives you a characterization of what are these limits. In particular, you get a proposition that has this form: if beta, so beta is the SNR. My model was x equals square root of beta over d, I think, w h transpose plus z. Okay, so if beta is less than a certain threshold beta base, let's call it of k nu delta, then for any estimator h, for any h hat w hat, limit dn goes to infinity. So here I'm looking at dn goes to infinity, so d and n are the dimension of this matrix with d over n, n over d equal delta fixed. Okay, so in this limit, if you look at, okay, let me write it and then I explain what this is. So you look at the correlation between the so this matrix, or for this matrix, is a matrix that is n by k. I project out the constant vector. So for instance, h perpendicular means h p perpendicular, where p perpendicular is identity minus 1 over k, 1 transpose. Okay, so I subtract from each row the sum of that row. This is completely uninformative. The sum of each row is just a dummy quantity, and this is 0 below that threshold. And similar for W. Now this threshold is given in this by applying these theorems is actually as a kind of complicated form, but we look at two cases in which it is simple. For k in 2 and 3, and u equal 1 and 1/2. So these are the cases that we studied. We find that this threshold is equal to the threshold of what would be the spectral method for this problem. So this is a simple formula: k nu minus plus 1 divided by square root of delta. Okay, so this is the first component, gives you the equivalent of the lambda equal 1 threshold. The second component is generalizing the variational inference algorithm. Okay. So I will not go again in detail. But turns out that this is simplified because, okay, again, as I wrote before, okay, we assume this decomposition. And these factors take a simple form. This qi of hi is really e to the mi hi minus 1/2 hi q hi times q0 of hi, where this is the prior. So basically the posterior at any you prove that at any stationary point of the KL divergence, the posterior or the belief is equal to the prior times basically a Gaussian density, where mi is related to the mean of this density, and q is a k by k matrix that gives the covariance of this density, and the same for the factor on the weights. Okay, so this is e to the some m tilde a wa minus 1/2 wa q tilde wa q tilde 0 of wa, where this is the Dirichlet prior. Okay, so this is the Gaussian prior, and this is the Dirichlet prior. So once you have these ansatz and you have this form, the optimization, you can see that the optimization problems reduces to an optimization problem over these vectors mi and this matrices q. Okay, so you write your KL divergence. Okay, this is, you write your KL divergence as of q hat and p of wh given x as some function log of some constant that is log of the probability of the data plus some function of what? M tilde, q, and q tilde. Okay? So these are matrices, basically. These are the set of all these vectors mi. So these are matrices in n by k. And this is a matrix in d by k. And these are matrices in k by k. So I will not write this formula because it's a bit messy, but can be written. And the variational inference algorithm is simply doing alternate minimization. So you minimize with respect to mq, and then with respect to m tilde q tilde. Okay. So what happens with this algorithm? Okay, so first of all, it has an uninformative fixed point. So there exists a fixed point of the form okay, let's say m star is equal to a constant times x times the all one vector times 1 transpose, and m equal m tilde star equal some constant times x t x1 1 on k transpose, and q star equal q1 times identity plus q2 j, and the same for q tilde star. Okay? So this point is uninformative in the sense that it has all columns equal. So it doesn't distinguish at all between the k topics. So this is a thing that is telling to you basically all the topics are the same topics. So it's answering basically the mean of all the rows of x. It's giving you the means of all the rows of x. So this is a completely uninformative fixed point or stationary point. A fixed point, I mean a really critical point. Okay, and then the following, the main calculation is computing the Hessian of this guy and checking when it becomes negative. And okay, so I will not give the formula, but there exists a formula that depends on beta, k, delta, and nu. So some explicit formula. takes a little bit of space, such that the following happens. If L is bigger than 1, then if you look at the Hessian of this function at the critical points, the uninformative fixed point, this has not just 1, but in fact theta of n negative eigenvalues, then with high probability eigenvalues. Okay. So this gives you the instability point of this variational inference algorithm, and this is also, of course, an instability of the alternated minimization procedure. Okay, so you can define a beta instability that is the smallest beta at which this happens, the smallest signal to noise ratio in which this happens. So this is function of k, nu, and delta, and the remark is that, okay, if this is an explicit formula, you evaluate it, you compare it with beta, the base formula, the base threshold, and this is below. So in this interval, variational inference is doing the same as it was doing in the Z2 synchronization problem, is giving an output that is, of course, uncorrelated with the truth, but is far from being uniform. Okay. So in the last 15 minutes, what I'll do is just give some, show how this instability shows up numerically. But final remark. You can modify. So this is something that came up a little bit before. You can modify this mean field free energy. So this factorized approximation and obtain a better. So this factorized form is what's called normally naive mean field. You can refine it, or you can improve it and get something that is called the Thouless-Anderson-Palmer free energy, and get something that has a better behavior and doesn't seem to have the same instability. Okay. So this seems to be stabler.
That's true for just K being 2 or 3, maybe not more, right? The number of topics.
In what sense? So okay. So for all the cases that we checked, so this doesn't have an instability. Okay, so I will not state formally the result, but doesn't have instability before the spectral threshold. Okay. So in the last, perhaps 15 minutes, I show how this result shows in simulations. This. Okay, so I want to do simulations, and here I'll do simulations assuming that the model is correct, right? As in all calculation, I assume that I generate synthetic data with the correct model, and I want to answer 2 questions. First, does variational inference converge to the uninformative fixed point? So what we do is something very simple. We initialize next to, close to this uninformative fixed point. We run variational inference. We get 2 estimates of the factors, and then we compute the distance from the uninformative subspace. So I'll do simulations just for k equal 2 for simplicity. And in this case, the distance from the uninformative fixed point is what? Is just the difference between the 2 columns. Okay? If the 2 columns are equal of W, means that basically it's answering all at 1/2, right? So if 2 columns of it's answering that each document splits 1/2 on all the ways. The same for the topic. If the 2 topics are equal, they don't contain any information. And this is a small, 1,000 matrix with various values of delta. And this is the beta, the signal-to-noise ratio, and this is the distance from this uninformative subspace that you converge to. So we run for many iterations, we have a convergence criteria, see what you get. One of these is for H, this is for H, and this is for W. So for beta small, variational inference behave correctly, it outputs you, something uninformative. But above beta, at this point is something around 3, they start becoming different from 0, and here it's very different from 0. And this is this vertical line is the instability that we computed, so the point at which this formula L becomes bigger than 1, and this is the threshold for the Bayes estimation. Okay. And this is basically the same kind of simulations in which, in a two-dimensional plane, we repeat this for 400 instances. For every point in a grid of values of delta and beta, and we look at the fraction of instances such that this distance is bigger than 10 to the minus 4. And on one side of this instability line, this fraction of instances is 0, and on the other side of this instability line, that is this black line, this fraction of instances is 1. So as soon as you move on this side, variational inference outputs something that is far from 0, and this is the line for the Bayes estimator, the Bayes optimal estimator. So in this interval, basically, variational inference is outputting something that is non-zero but has no meaning. The second question is the output of variational inference positively correlated with the truth. Okay? So how do we check that? Well, again, sticking to the case k equal 2, look at the informative component. So for instance, the difference between the two columns of the matrix H. This is the difference between the two topics, whatever is non-trivial. And then what we look is the correlation between this and the true topic, again in the non-core. And we have to regularize it a little bit not to get 0 over 0. Now, we want to check whether this is 0 or not. Of course, for small sizes, this has fluctuation and varies continuously. So what we do is, one nice way to check whether this is non-zero or not is to do this. So this is a physics trick. It's called the Binder cumulant. So we look at the fourth moment, the empirical fourth moment of this correlation divided by the square of the second moment. Well, this is an interesting ratio because if this is asymptotically 0, you expect it to be Gaussian, roughly Gaussian, with perhaps variance, a small variance. So the fourth moment divided by the square of the second moment should give 3. And I set my coefficient in such a way that I get 3/2 minus 3/2, so the Binder is 0. If this is non-zero, I should concentrate around something non-zero. So this should be roughly the same as the square of the second moment. So you get 1 by 1, 3/2 minus 1/2, and the Binder should be 1. So it's a nice way to start from a transition that is non-sharp and getting a transition that is sharp. And this is how it behaves for this simple instance. These are the two thresholds, and this is the instability. So here things are far from 0, and then basically this Binder cumulant is small and starts growing across, grows as a transition around the Bayes curve. Okay, and also here it has a transition. Also here for 4 different values of delta. And this is the heat map of the same quantity. So this guy start being correlated above the Bayes line. Okay. So this is the summary for variational inference. This is basically the same plane. There is this region in which the correlation with the true vector is very small, but the output of variational inference is far from 0. Now we can try to fix. I didn't explain, this top free energy, but this is kind of a different, slightly improved, variational approximation that again relies on similar hypothesis but does calculation better. I will not go in detail, but this behaves better. So the alternate minimization of this thing, the equivalence is this approximate message passing algorithm. So it's related to belief propagation. And this is now behaves better in the sense that is, this is the norm again. So the distance between the uninformative fixed point, this is very small until, or fairly small until the base threshold. Again, it's very small until the base threshold. It's very small until the base threshold, and it's very small until the base threshold. And if you plot the
dashed line now is the...
So the dashed line is always the instability of the variational method, and this is the base method that is also, in this case, the spectral threshold for the model. Okay? Now, if you run AMP in this case, this is a phase transition, so it's small. It doesn't, so the non-informative fixed point seems to remain stable until the right point, and then becomes unstable at that point.
You're not sure if that's the case exactly, or?
I'm not sure in the following sense. I'm sure in the sense that I can do the analysis using state evolution, which corresponds to taking n to infinity first and then the number of iteration infinity later. So in that sense, I'm sure. But I'm not sure in the sense of computing the Hessian. Okay, so the same proof doesn't go through. And in the simpler case of the Z2 case model, you can check that. But now computing the Hessian for the topic model is a bit messy because there are these Q by Q matrices. Perhaps it can be done, but we didn't yet do it. Okay, so I'm not sure really that the minimum, the critical point of the top free energy is really, a local minimum. But okay, to summarize things, we have some partial, rigorous evidence that this point is stable, and numerically it seems to be stable. And this is again the plot, and there is some numerical problem also with this algorithm. And the correlation for this algorithm shoot up at the right point. The correlation with the truth shoot up at the right point. That is the base optimal threshold. Okay. And this is the same thing plotted in 2 dimensions. This is the base optimal line. Here the correlation with the truth is large, and here the correlation with the truth is small, as it should be. Okay, so what is the conclusion? Okay, my conclusion is that, variational inference is very successful, but I think it should be taken, and it's a very interesting idea in the sense that it has the promise of translating, a base problem into an optimization problem. This is very interesting, but it has some problem. In particular, in natural cases, it can believe that there is a signal where there is actually no signal whatsoever, even if the prior is correct. So yesterday there were a couple of talks about what happens if the prior is incorrect, how you robustify machine learning methods, etc. Here the problem is more fundamental. Even if the prior is correct, things do not work as you would like to. And the last 2 slides I showed that this might be fixable, but of course, needs much more work. Okay. I think that's it. Thank you.
Questions?
So yeah, just to clarify what I was wondering. So since you're actually making most of your conclusions about the case where there's no signal, what you're saying is, correct me if I'm wrong, are you saying that if I were to do some posterior-based inference, for example, some confidence interval or something, it would actually predict some non-trivial confidence region for where sigma is or where those guys are, and they would be somewhere else? Is that
Yeah.
what would happen, basically?
Yeah.
Okay.
And so it tells you that the posterior. For instance, look at the case, the binary case, right? The Z2 case. What it tells you now, what is the posterior in this case? Is a probability distribution on 2 numbers. The right posterior is this, 1/2, 1/2, and what variational inference tells you is this, right? So this is what I call wrong.
Yeah, sure. But when there's no signal, I mean, when nobody can, from pure prediction perspective, when nobody can do anything, it doesn't really matter if my output is, oh, this thing should be all
But
one.
this is a method, but this is a method for unsupervised learning. So supposedly this discovers structures in data, right? And here we're seeing it, the structure that it gives is, in some cases, wrong. So suppose that you are trying to do clustering, for instance, in the Z2 model. So it tells you a partition of the data into two groups, right? In the Z2 case, it gives a partition into groups. And it tells you, okay, I have this confidence in this. That I have this confidence that this guy is, a Republican rather than a Democrat. Okay, and it tells you, and it's much better than maximum likelihood, because not only is telling me a partition, but it's telling me also the confidence. I'm telling the partition is wrong, and the confidence is nonsense, right? So now above lambda equal 1, well, if lambda is large enough, if the model is correct, you can do it anyway. Actually, you can do it with spectral methods, this problem, if the model is correct and if the signal is, So there is no really an issue. Now, what happens around lambda equal, about signal to noise, the critical signal to noise, I cannot really, tell you, but my guess would be that it's not perfect, or it's not as good as you would like. It's not optimal.
So when you say that it might be fixable with the tap-free energy, if the spike had a different prior, would it still be fixable, or for different priors it might not be the case?
Which prior? So for instance, it's very easy to see that this instability, if you use the tap-free energy in the Z2 problem, fixes it. That's very easy to computation.
I'm asking that if the spike, instead of being Z2, so that it has only plus minus things, if there were a different prior on the spike, then in those cases would...
Yeah, so the expectation is that it fixes it always, right? Now in this topic model distribution, this is this Dirichlet prior, basically. What we did is basically compute the state evolution and then check that this is stable. So, but this is not the full stability, because this gives you a finite number of iterations for n goes to infinity. Ideally, I would like to get a stronger result in which you really compute the Hessian and compute the spectrum of the Hessian and check that it is PSD. But that, I think it's doable, but would be interesting to do.
But here there is the added subtlety that the spectral and base are not the same if the prior is different.
No, I'm not saying, yeah, well, okay, but that is, not that relevant, right? I mean, for this is not that relevant, but because in any case I'm interested in algorithm. I'm not that worried with something that is not optimal accuracy, but I'm more worried about something that outputs a confident answer. And
Okay, let's thank Andrea again.